Is anyone else going to be showing up from the start?
I don't know.
No word from Katie?
No.
Okay. All right, then maybe we should get started.
Yeah, sure.
So you do have an audience online. There may be more people joining in. So we are getting started. Though, why is there feedback?
Is the streaming working?
Streaming should be on. Can you mute? Could you all mute, please? We're getting a lot of streaming. There we go. That's sorry, not streaming. A lot of feedback. Okay, so I think we're ready to start. So the speaker today is Arturo. He's from the CFA. He'll be talking about what I always consider Gaussian processes in supernova cosmology, but he says there's more to it than that. So okay, Arturo.
Yeah. So I'm going to describe some of the statistical tools that I use as part of my research. I have split the talk in two parts. One is very I'm going to describe some of the.
I think if you mute everyone.
What's my voice?
How do I? Something is going on here. Why is it?
Yeah. Well, sorry. I'm going.
That was you, right?
Yeah, it was me.
Okay. All right.
Yeah. So I have tried to be very introductory. So and some parts I will be very obvious for some of you and some other for others. But so let's start. So let me first talk to the people that is not astronomer to motivate what I doing as research. The idea is that in 1998, people here at Harvard discovered that the universe is expanding in an accelerated way. And they use some kind of star that when they explode, their luminosity is very regular, and we call those standard candles. Using this to the right, I have a galaxy where there is one of these standard candles, or these supernovae, exploding. And people observe this object, and from that infer distances, and from that they arrive to the conclusion that the universe is accelerated in its expansion. So people have been working in this more than 20 years, observing this explosion using the optical wavelengths of the light with telescopes. However, there is now people is getting in troubles because we have a bunch of data, but there is some systematic errors, uncertainties that start to dominate the constraint that you can derive from this data. So basically, these systematic uncertainties start to be so large that adding more observation of supernovae is not going to help to constraints to better understand the accelerated expansion of the universe and the reason of why it's expanding that we call dark energy. And one of the reasons that of these systematics is that the optical light is dimmed and reddened by dust that is in the Milky Way, is in the galaxy where it explodes the supernovae, and also in the middle. So this dust has been very problematic, and one possible solution to this problem is actually observed in near-infrared. So near-infrared observation is much less sensitive to this kind of dust compared to the optical lights. And here to the left, I've shown a patch of the sky observed in optical wavelengths, what we call in B-band. And to the right, the same patch, but now in a near-infrared band. So you can see how it's much more transparent, the sky in these wavelengths. So the idea is to use this kind of advantage of near-infrared for getting better determination of the distances of the supernovae, and then derive better constraints on the acceleration expansion of the universe. So one of my collaborators, Andrew Friedman, has compiled a bunch of observations of supernovae in near-infrared. Essentially, a good bunch of those observations come from here from CFA. Another group working on this is called Canary Supernova Project, and other people has been also reporting observation of supernovae in near-infrared. So now we have roughly 190 supernovae, where we have the optical and near-infrared light curves. And for the non-astronomers light curves, I mean this time series of data. Let me show next slice. Here in the x-axis, I have days. It's time in units of days, and this is magnitude. It tells us how bright is a supernovae, and this is for a single supernovae, and this supernovae was observed in different bands. In the top, they correspond to the optical bands. And this in the bottom to the near-infrared band. So you can see the colors. There's a shift that is put in the data, so we can better see the different points. So the idea is to use this kind of observations of this data to feed the data and infer distances. So the idea is use some kind of model, some techniques to fit all these points, and then make some additional steps in order to derive distances from these observations. In particular, I have been focused on using just the near-infrared bands. Let me go back one slide. So this near-infrared is, for me, correspond to Y, H, J, and K. There is no example here for K, but so what I have been working on is in this kind of light curves that this is in the invert the order, so the near-infrared light curves of time series of data are in this part, and they show a second maximum. And it has been, we try to use this second maximum also to observe the supernovae at later times when in optical bands the luminosity of the supernova start to decline. We have a second chance to catch the supernovae and their luminosity, but there is some random variation of the supernovae that we are trying to understand and implement in the model.
So what do you mean by inverted? I mean,
I'm sorry?
What do you mean by inverted? How did they get inverted? The magnitudes?
No, inverted compared to the previous plot. I mean, in the previous plot, sorry. I'm going, it's not working. Finally. Yeah, I just was saying that in this plot, I arranged the near-infrared bands in the bottom of the figure.
So the y-axis is not representative of the actual magnitude.
Yeah, it's the magnitude, but some constant that we add just to make some split, and then we are able better to see this difference between this red point and these yellow ones. And this.
Yeah, I mean, magnitude 40 is not visible. Right?
Yeah, and this is days, observed for days. I just was saying that in next plot, the near-infrared bands are in the top, but just very simple thing. So my goal is to infer distances from each of these time series of data. And I have my method I have implemented is there are two. I'm going to talk mainly in one of these methods. Is to first to create a template of what is the average lie curve or time series shape of the data. And then from that, I use Gaussian process regression to interpolate the data. And then I use a simple hierarchical Bayesian model to combine and then create this template. When I have the template, I feed the data just by minimizing the residuals between the template and the points. I'm going to describe these 4 steps in details now. Now the introduction was for no astronomers. Now I'm going to change for no statisticians. The audience that I'm going to talk now. So for a statistician, probably it's going to be very basic what I'm going to say, but sorry about that. The Gaussian process is a very start to be a very popular method to interpolate data or in a non-parametric way. And this is very convenient for supernovae because for the supernovae we don't understand the Taiwanese supernovae what is exploding. We have some models. People is working. People say that there are 2 white dwarfs, one dwarf, and the other is one dwarf and red giant star. A thing like that. But we are not really understand in detail how it's exploding. So we don't have a theoretical method to given this kind of observation, like here, when I have dates and absolute magnitude, we don't have a theoretical model that is going to tell us how these luminosities vary over time. So in this case, it's part of the motivation to use Gaussian process because I don't have to assume any particular model or underlying model, but I could use a non-parametric method that is actually what Gaussian process do very well. So I have the data. I'm going to explain a little bit more my notation. I call M. N stands for magnitude, absolute magnitude. Is one of these points, and it depends of the phase or the date that is observed. T stands for time. So at every time t hat, we have a data point M. The hat stands for theta, and S, I use this very unusual index just to refer to a supernova S. So every time you see an S, it's for a supernovae. For the R, I'm going to ignore for now. So I have this kind of observation in a given band. For now, it's not really relevant, the band. I'm going to explain more the method. So I have time and the brightness of the supernovae. So and the telescope observes this brightness, and this have this kind of shape. And now I'm going to use the Gaussian process formalism, where now I'm going to try to infer or interpolate or determine what is the absolute magnitude, for instance, in the middle of these points, and also in this region, and so on. So this determination that I don't know because I don't have data here is what I call M. Also, is an absolute magnitude, but it's at a given time t asterisk, where t I choose what's the value of t asterisk, and it's in the it's going to be in all these regions. So flowing more as a statistical language, we want to infer the apparent absolute magnitude, at a given time t asterisk, given the data that I already have is this guy, M at times that I know they are known values. This other time, so it depends of the datum, of the absolute magnitude that I already know, the times that I already know, and the times where I want to infer the absolute magnitude. And I assume that they have a Gaussian distribution where they are a mean value and a covariance matrix uncertainty that describes uncertainty and correlation in this data. So this expression looks slightly scary, but it's very simple. So we have the absolute magnitude where I want to infer the values, and I have all the things that I know, or I decide what values to choose. In my case, I decide that every half day, I want to determine this absolute magnitude. So this t is a vector that runs from, for instance, I start here is 0, 0.5, 1, 1.5, etc. It moves all to the region where I have data. Some questions here. So from that, the result that I'm going to obtain is this kind of interpolation, where now the mean value in my Gaussian process formalism is going to correspond to to this red line that is actually the best function, the function that better fit this data, and the covariance is going to at a given time is going to tell us the uncertainty in this determination that is in gray. It is gray band. So it's what I do. And there is some formalism to determine this mean value and covariance. This comes directly using the standard formalism for Gaussian process, where I have to choose a kernel that I'm going to show in a moment. And this is some equation that is a generalization of a Gaussian distribution. So the kernel, or this K that is called, usually has a kernel, has this expression that is on the top, where essentially the kernels tell us what is the correlation between two given points. So I have a point at a time t, at prime t. So this trying to give that quantify a correlation between 2 points that is the one that the kernel that I choose is the exponential kernel, where the correlation between 2 points get smaller when the points are more distant. So when, let's say, t is equal 0, t prime is 10, I have some value for this quantity, but if t prime is now 100, this quantity is going to be smaller and smaller if these guys start to be larger and larger. That larger, I mean that is more distant from this t. So in other words, let me go back. If my iPad allow me to do that. Yeah, so I have, let's say, for instance, this is t and this is t prime. The correlation is going to be by that kernel. That between these two guys, the correlation is going to be larger than this guy compared to this guy. So it's the basic idea of the kernel. I have to determine what's the value of this sigma k and L. They are called hyperparameters of the Gaussian process kernel. The way I did this determination is there's also a standard formalism or procedure to determine this sigma k and L in the kernel. Essentially, it's minimizing the log likelihood of the Gaussian process. But I wanted to use all the data, so I determined 2 values for all the sample, because the opposite way will be that I determine sigma and L for every single supernovae. But but all those supernovae in a given band, for instance, Y band that I was showing, they have to be more or less the same kind of sigma L and L, sigma K and L. So the idea was to use that hint or that physical situation in order to compute these two values, but using the whole sample. So instead, just that's to the usual expression that we have for determining these hyperparameters. You can see this summation at the beginning of the right part of the right-hand side of equation A6. Yeah.
So you want to determine the posteriors on sigma k and L.
Yeah.
Don't you need to make I mean, this looks like a likelihood.
Yeah, sorry. Yeah, it's a likelihood. I just minimize the likelihood, so I don't really compute the posteriors. Yeah, it's a likelihood, maximum likelihood determination. Just minimizing this expression. But I don't know if that's your question. Answer your question.
Yeah, that was the question. I mean, I was going to ask what priors were you using.
Mm. Yeah, but yeah, I remain just at the likelihood level. Yeah. So I get out from the formalism and all those equations, just to continue what's part of the procedure I'm doing for derivative distances for supernovae. So using this technique of Gaussian process, I determined this kind of red lines and with the gray bands in different bands. That are the near-infrared bands, and then yeah.
So just to be clear, you estimated sigma and L from across all supernova for a given band.
Yeah, correct.
Okay.
Yeah, that's it.
And you did that for several bands.
Yeah, yeah. That's a very good point. That to say that this equation A6 corresponds to a given band, but for all the supernovae that I have in the compilation. So actually, given that I have 4 near-infrared bands, I have 4 equations that I minimize separately. Yeah.
Doesn't that mean that you have to worry about redshift and correcting for the bands and all those nice things?
Yeah, I put the data in the rest frame time, where I correct for time dilation, and also in the absolute magnitude frame, so everything was comparable. Yeah. So I taking into account the redshift for every supernovae, and also important to mention that I working with a low redshift sample. By redshift mean that are nearby objects to the Milky Way or galaxy. But the idea is to combine this kind of supernovae with very distant supernovae, or what we call high redshift, and then make some cosmology. I mean, determine the properties of the universe. So once I have this for every band, I here just an example, 4 examples of a bunch of plots that I generate when I fit or interpolate data. So the idea now is to use a template. In the second part is to create a template from these Gaussian process determinations. I'm going to first explain the idea, and then I'm going to move to the formalism. So let's say here I'm showing all these the different mean values in the interpolation that correspond to the red lines in the fits that I presented 2 slides ago. For a given band, it is correspond to Y band. So if I normalize to be 0 at day equals 0, this is just day in a fancy way, but it's just days, this x-axis. So if a day equals 0, I normalize to be 0, the absolute magnitude, and overplot all these lie curves, I get this kind of plot. The idea is to understand what is the shape of the lie curve, regardless of the absolute magnitude, just understanding the shape. And also, just to mention that this day equals 0, what it is. And it is when it's the maximum in luminosity in one optical band that we call B. So let's just imagine that I have in the B band, and it will correspond to this point. So in other words, the near-infrared luminosities of the supernovae turns out to be brighter slightly earlier than the optical band. So the near-infrared has roughly -4 days. They have their peak luminosity compared to the optical bands. But I'm still using the optical B band as the reference because it's a standard way in supernova cosmology things to set the time. But so I have this bunch of light curves, and now I'm going to combine all of them. First, let me show how they look, not the mean value, but the bars, the gray bands that I was showing. I just wanted to understand what the shape of these light curves. And then I use the hierarchical model to combine all these light curves using the mean and the bars, I mean the uncertainty in the mean, to derive this template. In this case, it's still an example, Y band, and I get this kind of shapes. So this tell me what is the shape of the light curves for all the using all the supernovae that I have in my compilation.
So what you're saying is that for the previous plot, and you ran a GP on that one to get this one? You ran a GP on this?
No. Now I have already run a GP, a Gaussian process for every single supernovae, and here are all the supernovae that I do. Yeah, so let me go back slightly more. So in a given band, for instance Y, I fit all the data using the Gaussian process, and the red line, I mean the mean in the fitting, it corresponds to each of these color lines, even more back. So I mean these red lines in different bands, for instance for Y bands, I have this red line and green band, and here what I have, this will correspond to the red line, sorry, but I put different colors now for better distinguish. And this corresponds to the gray band. Yeah, for all the supernovae in a given infrared band.
So what's the next plot?
And then I use the hierarchical model that I have not explained yet. I just trying to first be more intuitive to combine all these spaghetti things and get this kind of template that reproduce or tell me what is the typical or average shape of the light curves in all my compilation. In a given band, I have 4 bands, so I have 4 this kind of shapes. In this case, the black correspond to the mean Gaussian process. In blue correspond to the uncertainty in this mean, and the gray band, the standard deviation. That is part of my hierarchical model. And now I'm going to jump to the formalism, how to determine this plot. But is it clear so far?
I think so. What sort of concerns me is that again, going back to the previous plot, there is a lot of structure there, right? Which doesn't seem to be picked up by the next one. In the gray bands, and for instance, at phase of 10, you should clearly be seeing a bimodal signature. Also at time phase of 35 or so. But in the next curve, you seem to have a unimodal profile at every point.
Yeah, that's a good point, and that's one of the things to improve in my model, in my method. let me rephrase that. I'm deriving just a single template at this fix, but here we clearly see a lot of variability in a given time, even in this row, in the second maximum. I mean, second maximum seems to be that in some cases is at given time, and some other supernovae is much later, until like that. And the template method is not encapsulating of this structure. Yeah, but it's work in progress that I consider to now create not fixed, but a variable template that it's better adapt to each liker.
Just so we have a better sense of what's going on in here, is this variation in individual light curves like an expected physical thing? Is this due to measurement error? What is causing the bimodal distribution? Do you have a sense for this, or is this part of the question you're trying to answer?
You said optical, but do you mean the near infrared?
Sorry, if I said optical, I didn't mean to. I'm just curious about the physical origin of the variation here. Do we expect everything to follow the same line, or?
Yeah, well, it's part of the research to understand what is the shape, what is the variability. So it's part of the result that we were observing. There are previous results that have been already shown and found that there is this variability especially for instance, in the second maximum, that it happened at different phases. Even when you have corrected everything to put in the same restraint, etc., there is this variability. What I have found, and also previous results have found, that where there's smaller variabilities at the first peak in the luminosity. But after that, it starts to be this crazy thing that is very hard to model. It's part of the challenge that we're trying to do, and we don't understand at the physical model what's exactly causing this variability when the supernova explodes. I mean, second.
We don't know why. That's why we're using GP.
Yeah, exactly. We don't know. We don't have any model say given these properties of the supernovae of the white dwarf is going to explode at this phase or whatever. We don't have that information. We don't know. Yeah. So now let me show how I do this template. The first level of my hierarchical model is assume that for a given I'm going to make this hierarchical model at a given phase or a given time. So it's going to be a bunch of slices. Let me go back for a moment to say what I mean. Let's say I have a cut at day equal 20. So I'm just going to consider all the points that are at day 20. So I ignore all this part, and just all the points that I have this point at this day. I do have this point because they are the Gaussian process fit. These shapes are not the data. They follow the data, but they are the Gaussian process fit. So I have total control at what time I have these values. So at a given phase, I have this. This corresponds to the Gaussian process interpolation at that phase. For this moment, I ignore the time because it's going to be a different time. But at a given time, the time is fixed. So I assume that it has a normal distribution, where there's a mean value, and for this in this normal distribution, and standard deviation or a variance in this Gaussian distribution. It's an assumption that I do. And then the second level is now assume that these average or mean values that I have, that I denote with this tilde here, they are going to be distributed also in a Gaussian way, where I have I have a mean value for all these absolute magnitudes, and also a variance in this M. It's going to happen, or turns out that this M script and sigma script is going to correspond to the template. Is what I want to determine. So let me motivate all this, why I'm doing this why I'm following this path. So I have the determination from the Gaussian process for a given value. But I'm going to, what I want to use with this hierarchical model is to borrow strains, or to borrow the power that I know for other supernovae what's the value. So I want to predetermine what is the average value for a given supernovae in a given time, but using the power of all the other supernovae at that given time. So it's going to, that is going to help me to shrink the data and to have this middle point between pulling all the data and just having independent determination of the data and a given phase. So that's the idea of the hierarchical, or that's my idea behind why to implement this hierarchical model. So use that power to borrow strength from the different supernovae at a given phase. So I have, so let me recap. I have, this is the Gaussian process, a point, the red, one point in the red line, on the red curve, and I'm going to compute this M, you know how to say, hat, or yeah, tilde, tilde, yeah, tilde. So I'm going to recompute its value based using all the data at a given phase, and all those values at a given phase I'm going to combine, assuming that they are Gaussian normal distributed with M script and sigma has a variance. So graphically or visually, that's the idea. So now M is going to be the black line. One at a given phase, for instance, this phase on which I have the pointer, this corresponds to M, and sigma corresponds to the green bar. The blue bar corresponds to the uncertainty that I am able to determine for M. For these two guys, I determined its values and their uncertainties. Any questions here? It's more or less clear. So I do the same for all the different bands. I was showing just Y band, but I repeat the same exercise in the different bands. In all cases, it's normalized, so it's natural and obvious that, or expected that at phase or day equals 0, all the residuals in this template is 0. That's by definition, by construction in my template. And then I start to be these broader bands basically because there's this different behaviors of the Likers between different supernovae. So let me jump this one. Using this template, now I'm going to take the task to determine the inferred distances. So what I'm going to do is this template and then have the actual data, the Likers, and minimize the residual between the template and the data to determine what the best match between template and data, and then use that information to infer what's the magnitude of the Likers at phase equals at day equals 0. I'm going to explain that in a moment. But first, let me set that when I was doing this fitting the data using this template that I have built, I realized that using the whole template sometimes create, the whole template, from roughly -8 days to 60 days after the maximum in V-band explosion. I realized that there's some, using the whole template fitting the data, it creates a larger scatter in the total distance modulus that I'm able to infer. Probably it's going to be clearer a little later that I'm going to explain more about the Hubble diagram. But so I investigate what's the best portion of the template to use to feed the data, given the data that I have, and it turns out it's roughly around 30 days. So using the template from -8 to 30 days is the best time where I have this minimum, where these correspond to days and these correspond to the root mean square in the scatter in one final result that I'm going to show that we call the Hubble diagram. And if I use just a small portion of the template, let's say for here, in all cases, start at -10.8. Let's say I use from -10.8 to day 10, this small portion of the template, and I feed all the data, and it turns out that I get this blue line that corresponds to the RMS that increase, or it has a given value, and it keep increasing and get a maximum. If I use now a different, larger portion of the template, and then get a minimum, that is what I want. I want to get the smaller value in RMS, and this is and 30 days when it happens. So is when I get this decide to use just that portion of the template, and also in terms of how many supernovae I was including. So if it's in red, the number supernovae. If I just a small portion of the supernovae, small portion of the template, I will just my sample will reduce because there are some supernovae there is no data around this region. But if I increase using the whole template, there's a moment where I'm using all the data because it covered all the region where I have data in the light curves. Yeah.
So,
yeah, sure.
so that blue curve that you have, isn't that limited by the green band that you have in your model? I mean, you can't ever find this RMS smaller than the green band, right, by definition?
Yeah.
Right, the lower part of in the lower window.
Yeah.
The green band that you have sort of sets the minimum uncertainty that you can have when you do any sort of template matching, right?
You're saying that using this region where I can see that is the smaller.
Yeah, and as you go to longer and longer phases, that width that you have is the smallest uncertain, the smallest residue you can have for any template fit.
Yeah.
Right?
Yeah.
But that doesn't seem, I mean, you seem to be getting smaller RMS when you do the template matching. So I'm not quite sure how that works.
I think I understand your question.
So if you go to the next one, go to the J band. So in the J band, for instance,
This
sure,
here?
yeah.
Okay.
The green band goes to around 0.2 plus minus 0.2 around 20 days and goes up to plus minus 0.4 at 40 and 50 days.
Yeah.
So now if you go to the next slide.
What I was showing.
This one. So the blue curve that you have is significantly smaller than the green band. So how do you manage to get an error smaller with template matching than you have in your original model?
I'm not sure if I understand, but let me think. So you're
So from there, you're using days increasing up to 30 from minus.
yeah,
minus
exactly.
8.
I usually essentially this part.
Right, and so there the band is narrower. So the average error is the average error across all that time is well below 0.2, or average standard error is below 0.2, right?
Oh, you're
Because you're averaging across time. Is that that was my impression?
Are you
Is that
averaging
right?
across?
Uh,
No, but then go to the blue curve. The next one, the one after that. Yeah, this one, right? So this okay. This is the part that's confusing.
Yeah.
So, all right, maybe I misunderstood what you're doing with the blue band. What blue curve? Can you say that again?
yeah, the blue one.
Yeah.
The blue curve is the RMS.
From the template fitting.
Using the template to match the entire sample.
Right. So okay. So now I'm still confused. So the template itself has a quote-unquote systematic uncertainty of 0.4 magnitudes at 40 days and higher.
Yeah.
But that's using the template from -8 to 30, say. So the blue.
No. So
The blue.
I mean, think of it as this is the model that is being used, right?
Yeah.
So you derived a model, and the model has a certain uncertainty,
Mm-hmm.
and you're taking this model and fitting it to data. So whatever statistical uncertainty you have, it must be compounded by the quote-unquote residual systematic uncertainty that's still in there, right? I mean that, or maybe I'm not looking at it the right way.
Can we think of it sort of, if we have a line that corresponds to one particular supernova, it would land sort of somewhere along, say, the J band,
Anywhere in
right?
the green band.
Or anywhere in general. Or yeah, but it would be likely around the green band because that's what we use to fit that green band, right?
Yeah, actually, let me show you the plot, one of the examples.
Oh yeah, great.
Okay.
So the red dots are the data, and then you fit a Gaussian process maybe, and it would land kind of along. For the green part, it would land part around the green part, and then it would extend to the right. The template fit, as far as I understand, as long as those values are reachable with the Gaussian process and the systematic error, meaning we can draw a Gaussian process line that would land along those points, the error will be small. Because, does that make sense?
Maybe.
So as long as they're reachable, because if you have points like, say, on the bottom left plot, there are some points that look like they're going to land kind of outside of the band.
Mm-hmm.
Those are going to have higher errors, higher MSE, because the Gaussian process or the curves that would reach them won't be able to systematically.
Okay, so the way to look at those blue curves in the previous plot is as additional RMS compared to after you remove the GP.
Yeah, I think so. Yeah.
Yeah, I'm trying to understand exactly what you're saying, but we could discuss.
Okay, all right. Yes. Continue.
Yeah. Yeah. So using this part of the template, I get this kind of example of fitting Likert to the data, and what I want for this template fitting is to infer what's the apparent magnitude, or what the luminosity of supernovae at phase equals 0. See, it's still my reference time. So in some cases, the Gaussian process thing will do the work by itself. For instance, in this case, I didn't show the Gaussian process fit, but fit very well and follow the line. So using just the interpolation of the Gaussian process, I will be able to determine what's the apparent magnitude at this point. But in some other cases, in some other supernovae, it's not the case. For instance, here I'm missing data. And the first point that I was observed for this supernovae was roughly at day 4, and so on. In these cases, even it was after 10 days. So it's when the template is helpful to infer or to extrapolate what will be the uncertainty in this, what will be the value in the apparent magnitude at phase equals 0. Well, I will show how it's. Or let me back. I will say that. In these cases, the green band is considered is taking into account that if the data I'm fitting here in this part, in this phase, in this region of the light curve. The template has more uncertainty, so I'm going to account for that uncertainty. So the closer I have points around maximum, I get the template smaller, the uncertainty in the template smaller, but in this case it's larger. So I have to take into account I do that. So the distance I determine is as follows. I have the template, I have the data, and I have what's the apparent magnitude at phase equals 0 or day equals 0. So I know this m script, I know this m is data. This is unknown, is what I'm going to determine, and I'm going to just I'm going to do that minimizing the log likelihood, where I have this vector where t corresponds to different times where I have data, and minimize where I have this covariance matrix given as follow. Here correspond to the green band at a given time, where it's time I and t, or time I and time j different. So when they are equal, they just are the variance of the green bar at that time. And this is times the exponential, the part of the Gaussian process exponential kernel, just to account for the correlation that there are in the data, in the light curves. I mean, at the different times, the data is correlated. It's not completely random. They follow a shape. Actually, the template is telling us that there is a shape. There is a correlation between the data at different. So, a datum at a given time is correlated to another datum at a different time. This expression tries to encapsulate that correlation. And when I use L with the same value that I derived from the minimization to determine the hyperparameter in the Gaussian process kernel. That's where I use all the data. And this just corresponds to the uncertainty in the estimation of the apparent magnitude. So this expression can be it's easy to do the math and get an analytical expression of what's the minimum of this equation 13, and I get this analytical expression. What's the determine absolute apparent magnitude at phase equals 0 and its uncertainty. So the final part to the derived distance is what I do is to use the apparent magnitude I have just computed in equation 16 and subtract the average magnitude of in the absolute magnitude at that phase. Let me go back a little bit just to see what I'm saying. So this corresponds to the average that I determined for different bands is Y, J, H, and K. So the average is going to be the I'm overfitting red line, and it's just the mean of this Gaussian. It's a Gaussian distribution, this red line, the red curve. This corresponds to the what I compute the apparent magnitude at phase equals 0 minus a theoretical distance modulus that I use. I determine using assuming a cosmological model. We are not. It's irrelevant the assumption of my cosmological model because I just determine the mean magnitude, and also because I using a nearby supernova compilation, so it's not high redshift. So moving forward to this point, so it's that's my final result that it's what I wanted to get this distance modulus for every supernovae and its uncertainty. And then I determine something it's called the intrinsic dispersion. That it was expression proposed by Casey Mandel, that is now in this talk, and Kirchner and Stefan Blondin. Where it's essentially the idea is to have this parameter to quantify what's the scatter in the Hubble diagram that I'm going to show in a moment. Once we subtract or we account for peculiar velocity in each supernovae, I'm going to mention say some words about that in a moment, and the uncertainty in the apparent magnitude at the maximum that I have just computed. About the peculiar velocity from astronomers, it's just the uncertainty that we account when the supernova is located in a given galaxy. The galaxy has some motion with respect to us, with respect to the CMB, and some intrinsic motion that we don't know for sure. We don't have a method to, or we try to measure, but there are some uncertainties in this that we have to account in the motion that I have the supernovae, given that it's in a galaxy. So I just going to jump to the Hubble diagram that I had mentioned several times, and is where I'm going to use this intrinsic dispersion quantity to determine what's scattered in these residuals. So the Hubble diagram is essentially put together all these distance models that I have combined, and it's the result that I get for the different bands. And here the residuals. The residuals are combined. I compute by subtracting the theoretical distance modulus to what I have just computed. And this is the kind of intrinsic dispersion that I get in each band. And for instance, in this case, I get 0.09 and so on. For the different bands, I found that the band that has the smaller intrinsic dispersion corresponds to H band. Just to say that I'm interested to have the smaller values in this intrinsic dispersion. Is something I interested to know. I cannot control what's the intrinsic dispersion. I just compute what it is. But it's desirable. It's what will be ideal to have the smaller intrinsic dispersion possible in all these diagrams. Because for astronomers, that will mean that the supernovae are much better standard candles. In other words, that are much better to derive distances to very distant objects. So it's something that we want. We want to somehow to measure distances at cosmological scales, and using supernovae that's the goal. And the smaller intrinsic dispersion will mean that they are much better standard. I mean, the luminosity is much more similar between different objects. I'm probably going to skip this part. It starts to be too long, my talk. I'm going to jump to the combining multiple near-field bands. I show the Hubble diagram for different bands, but one idea will be combine the data, and we did it in a simple way. I have estimated the distance modulus in each band. So this column in this vector 25, equation 25. The left part corresponds to what I have determined from the template method from the different bands, and I create this residual between what I obtain minus what it would be a total distance modulus, because regardless of the band that I use, I mean Y, J, K, OK, the distance modulus is physical, so it has to be just one single value. So in all cases, I subtracted this value, and I'm going to determine what's the value of this sigma, this delta distance modulus hat that I have. So I just did very simple. I determined what's a covariance matrix from this from the data using the different using the 4 bands, and from that covariance matrix that I need to write down, but. I created this log livelihood equation 2026, and I minimized this the expression to get this value, this distance modulus hat. That is what I want to infer.
So I have a question.
Yes.
In that covariance matrix, is it diagonal?
No, it's not diagonal. It has elements out of the diagonal.
Where does that covariance come from? Is it part of from the Gaussian process model?
Oh,
or not?
Sorry. No, it comes directly from all this data. I mean, they are not exactly like a Gaussian distributed. I just grab all this data and determine what's the covariance in this data, and it do have some terms, the matrix outside of the diagonal.
Filters overlap.
Sorry, say it.
The filters overlap. Oh, okay.
Oh wait, filters overlap. Oh right.
Yeah, that's
But
right.
that's not taken into account. That can that be taken into account in the Gaussian process model itself, or no?
The filter overlap. At least I'm not doing that. Probably, it's something it would be possible, but I don't.
There are no simultaneous observations, right?
Sorry?
Are there any simultaneous observations in the different bands?
Yeah. Yeah.
I mean, they're not just contemporaneous. I mean, you observe with one filter, switch to the other filter, as opposed to simultaneous observations that span, that you.
Yeah, actually, well, these time scales, the observations are very short, so they will correspond to observe the same supernovae at a given time, but in different bands. Strictly speaking, it's not exactly the given time, at the same time. There is some minutes or difference.
So you say you get U and then you switch.
Yeah,
B
just
and then
change
you
filter
G
and observe.
Yeah,
exactly.
At least. So you're not, at least there is this. I mean, you're not looking at the same data over and over again.
Yeah, but it's pretty close.
It's very close.
Yeah. So I'm getting to the final part where I show what I get using this combined method to the distance modulus. To the left, I show what I get using for a given supernovae that I have data or was observed in these different 4 bands, near-field bands. I use the covariance matrix and then minimize the expression that I showed before. I derive distance modulus. But there are some cases that supernovae were not observing before, just were observing 3 bands. So I repeat the same exercise. I derive a covariance matrix just using the 3 bands and derive its distance. For some other just 2 bands, and some that just have observation in 1 single band. So that's why I put any. So some of these supernovae have different bands that were observed. And I get this intrinsic dispersion 0.09. In this case, and some other cases are more strict, so I just use those supernovae that do have observation in these 3 bands. If it's not the case, I ignore and so on in these other situations, and I get for this combination 0.05, 0.09. But they are just numbers. Going back to the to my research for a little moment, what it means, is it good, it's bad? So it's what I'm trying to understand what these values will mean for my case. So what I did, I just recap that I'm working with near-infrared data, but there are people have been working for more than 20 years using optical data, and they're already very, very well standard software to fit the data using different methods. So now I do the exercise to fit the optical data for this supernovae to understand the scatter that I obtain, the intrinsic dispersion that I have found. So I just give a quick sample. There is a standard package called SOL2 that fit optical data from Type Ia Supernovae, and they are the kind of fit that it's create. And there is another one that is called Snoopy, and also just fitting the optical data. So that's why I have just this line fitting these 3 lines, because it just correspond to the optical bands. The other ones I ignore during the fitting, and create the whole diagram and determine the intrinsic dispersion to see what it means. What I get, and I get these kind of values. For using SOL, that is one of the most known and robust methods to fit light curves for Type Ia Supernovae. I get intrinsic dispersion of 0.15 and Snoopy 0.04. That is larger compared to the near-infrared bands. It means that optical bands show this larger scatter and are at least or equal or probably less standard candles compared to the near-infrared bands. Here I summarize some of the observations, but probably too much numbers. But yes. Here are the intrinsic dispersion that I had computed, and also the weighted RMS, because there are some caveats about how you define or what value you assume for the particular velocity of the intrinsic dispersion. So I try to move on a definition that doesn't depend on that value. I report these 2 columns, and in either both situations, it turns out that using just the optical bands for a given set of supernovae, using exactly the same supernovae, I get intrinsic dispersions for the near-infrared cases that are smaller compared to the optical bands. So that means that the near-infrared supernovae observed in near-infrared have more standard, or at least equal standard candles than near optical bands. But I didn't mention that for the optical band there is a bunch of corrections, or at least 2 important corrections that have to be applied to the data to standardize the supernovae. Usually people say that Type Ia supernovae are standard candles, but actually they are not. They are standardized. But optical, in the case in my analysis, I didn't apply all these corrections. It's just almost the raw data, just making some cuts, and it turns out without any of those additional corrections, I get in a very good scatter in the whole diagram. So it's something very promising. Just first, the last one. I work in this research is part of the larger program that we are working also with high redshift objects. We already have 23 supernovae at 0.3 and another one at 0.5. And with Robert Kirchner is the PI, and we have already finished observe, and now we are working on that. The idea is to combine all. This is the Hubble diagram now. This is the redshift, this distance modulus, and all the samples that I have been showing correspond to these red points in the Hubble diagram. And for these supernovae that we call raisins, they are in this range of the Hubble diagram, and with that we are able now to do additional step that is to fit this line that corresponds to the cosmology, and this is when we start to research about the universe. But this is a work in progress, and I finished. Well, just mention that near-infrared has summary are very good compared to optical lighters. We have the recent program, and there's a satellite called WFIRST that is going to observe Type Ia Supernovae and other stuff that we have to get ready for working with the data we have. Thanks.
Okay, so any questions? We've been interrupting you all along. I'm not sure that.
And try not to expand too much my talk because we start a little later. Yeah.
If there are any questions from the remote audience, now is a good time to ask. Not? Yeah, so I still don't quite understand how your those
The template.
Yeah, the template fitting works better than the uncertainty in your model. But maybe I just need to think about how it is that it's being done. Maybe that's fine.
Yeah, so I think I have a question about I think it's related to yours. So the template fitting, when you went from like that spaghetti plot.
Here?
No, way far back.
Okay.
When you were first introduced the template, I think a couple more back. A lot more back.
Yeah, my iPad's very small. It's very slow, sorry. It's like iPad 3, so it's still alive.
So a little bit more, I think. 2 more. 3 more. Okay, so
Here.
1 more.
Okay.
I guess another. Here. Okay, so in the previous plot, actually, you had a bunch of these error bands. There you go. And so you standardized them to be in the optical max at time 0, and then they had this sort of trend where some of them spiked, around 15 days, most of them around 25, some of them around 30. And then in order to combine all of these into one template, you, as far as I understood from the hierarchical Bayesian part, basically made it so that at a given time you have normal noise.
Yeah.
Right? So, and they have a shared mean and a shared covariance matrix. So that's kind of like another Gaussian process. But when you do that, you're losing this sort of this secondary structure that says that the max can happen at 15 and it can happen at 35. I think what it would say is that it'll just happen where most of them happen. So like, if there is a secondary max, it'll happen at 25, which is, if you go on to your next plot, that's what it sort of says, because it's averaging across all of those.
Yeah, exactly.
So you're losing the structure. Is what I'm concerned about.
It's like for a moment, for the hierarchical, I just take the data that lie in the rule, and then combine using the hierarchical model and get a value. and then move a little bit and just the data that is like in the rule and so on. So yeah, certainly I just getting like at some kind of average at a given phase, but I'm not really accounting for this variability also where second maximum is happening. Yeah, it's limited this method, but yes, as I mentioned, I consider to have an additional step to get something flexible that better follow this variability for each supernova.
And also the fact that, you know, if it's from these bands, and you kind of get the sense that your overall average curves seems to stretch out the second maximum, whereas in each of the individual ones, the width of the peak is narrower. And we go back to the previous one so that you can see it clearly. So something that starts peaking at 20 seems to have dropped off by 35, and something that starts peaking up at 30 or so is peaking off roughly 15 days later. Whereas in your overall mean curve is much broader.
So something that in connection with that I'm considering is by definition, by construction, I decided that at phase equals 0 is going to be 0. But what's happening now, I normalize at phase equal -4, for instance, or determine somehow the maximum of each near-infrared band, and then normalize that at the first peak, whatever it happens, I'm going to normalize that point. So this template or these shapes are going to align differently. Also, if I now use the second peak to normalize, determine the second peak, an additional step, and then overlap all of them to be exactly the same at the second peak. And now I'm going to find some scatter around this point, the regions. What I have in mind is to do that exercise and see now what's the best phase to normalize the template and use it to derive distances.
So, yeah, anybody is allowed to ask the question. I mean, David is asking, who's asking the questions? You're welcome to ask any questions if you have them now. I have the Jitsi thing up and running, so we can hear you if you say something. There is some mismatch between this and the YouTube, so they're behind 30 seconds or something.
So going back to Vinay's question, the template. So because you're averaging sort of, for a given time you're averaging all of the things. So I get that your that peak is stretched, right? So that kind of makes sense to me, that the peak is sort of long, has a wider amplitude than the actual data do. And what that sort of implies is that if you were to, so if you're using this as a template for what do light curves look like, all of them are going to be systematically off in that way.
Yeah, that's what actually I didn't use that part.
Right.
That's why that was motivation of my investigation, that this part, given that they have different second peaks, they in some cases my fit get worse if I use all the data that it was in the region, if I just use this part of the templates. Yeah. But I don't know if that's more or less in connection with.
Yeah, that makes sense. So then,
sorry, I mean, I was just going to say that it helps with the J band for the second peak, but there are still the same other things happening, even in the minimum, for instance, right? Maybe not in the minimum.
It's a little more
I mean, there's going to be systematics. That's right.
Yeah.
It's probably what.
But all of them have larger error, or larger. It's not like that. That band isn't error. It's like disagreement between the different fits to the supernova, right? Like the green band is kind of like how do these light curve fits disagree with each other? Is that a good way to interpret the green band?
I will say there is an additional thing. Is this corresponds to the green band, but it corresponds to the distribution of this n-tilde. It's not exactly the Gaussian process mean, but it's what I predetermine using my hierarchical model. Let me go back.
Sorry, we can't hear. Is that a question? We can't hear you. David? Yes. Go ahead. Oh, you can turn off the. You can get off the YouTube.
It seems to me that if you go back to that slide you were showing us a moment ago, what you were giving us is something like error bars on the mean function, which is not really what you want, right? You want errors that somehow.
Yeah, turn down the YouTube volume. That
capture the variability among the light curves. Right, and those error bars that you're showing us don't do that, which is pretty clear when you look at the plot of the multiple light curves. It's the kind of Lewis thing, but the variability among the light curves is not captured in the vertical variability at each time. It's quite a bit more complicated than that. So if you're just looking at that mean function, you're losing a lot of structure.
Yeah,
by forcing the data to fit that mean curve that misses so much of the structure, I just don't quite understand how you think you're going to get good estimates of the parameters.
Actually, yeah, that's a good point. It's something I already considered. It's also Binay's what one of his comments is about. And my answer to that is that this is like a first step in working on inference distances from supernovae, and it turns out that it works reasonably well. But yeah, there's additional step like accounting for this variability in the first and second peak in the first row. That is something that I have been also thinking about and make some preliminary analysis. But yeah, I completely agree that my method is to have a fixed template is not the optimal option or method to work.
So what is that?
Sorry?
What is that? Sorry, what is what?
Is it with a time delay? It's like we're talking out of time.
Maybe we should turn off the YouTube. Hang on a second. I'll have that YouTube thing turned off. You can start using just the
understand that there's a 15-second delay, so if I ask a question, it's about something that happened 15 seconds ago.
No. Okay, I'll have the YouTube off.
Yeah, you can still hear it. So Dave, were you asking about the? Can you see the Jitsi? Wait. Yeah. Okay. Yeah. So can you see the Jitsi? Turn off your mic.